you could spare some time from your absolutely busy schedule, because I know Akhil is working with you to talk to this young audience. Hopefully, it will produce some quantum scientists out of them. They're young people. I'm truly, happy and thankful to you. So, I'm sure by now you people have looked up Professor Nakamura's work. Really remarkable experiments, and you have already heard Akhil's talk. Professor Manudas was also mentioning about Professor Nakamura's work and some kind of future program which they have in mind. Now, Professor Nakamura is associated with RIKEN, if you see, and is a professor in University of Tokyo. And if you see his work, is basically IBM quantum computer you have heard so far, because there were a lot of industry academia interaction. Professor Nakamura has been developing this flux qubit, through which very systematically. I remember reading one of his Physics Today articles. There was this 1 over F noise, whatever is the origin. My first introduction to this was through his Physics Today article. Now, so we are very curious, because we have heard about from the IBM how they are working. We are very curious to hear you. And if you see, he has had almost all the awards. Like, for example, 2020 he became a PS Fellow, Nishina Award, and because my professors who were in Rochester and City College were from Japan, Professor Bunji Sakita and Professor Okubo, I know about the meaning of these kind of awards. So thank you, Professor Nakamura. You can please share your screen.
Okay, thank you very much for the very kind introduction. So yeah, let me share my screen. Yep. Okay, so yes, thanks again for the kind invitation to the summer school. So it's my great pleasure to give a talk here on our research activities and on superconducting quantum circuit. So yeah, my name is Yasu Nakamura. I'm now a director at RIKEN Center for Quantum Computing and also a professor in the University of Tokyo. So yeah, today I'd like to discuss about microwave quantum optics in superconducting circuits. But before starting, let me advertise our new research center named Research Center for Quantum RIKEN Center for Quantum Computing. So this we started in this year, April. So these are team leaders in our research center. So we have about 14 teams working on different topics on quantum computing, both experimental and theoretical. And so our research topics is covering superconducting quantum computing, in which I'm involved, and optical quantum computing, led by Akira Furusawa. And we also have several other groups, experimental groups, working on other quantum platforms like semiconductor spin qubits and cold atoms and like electrons on helium and so on. And we have several theory groups working on quantum computing theory and algorithms and quantum software. So yeah, this is a new center, and we are looking for good postdocs and good students. So if you are interested, please look at our website. Okay, so yeah, today I like to discuss about, microwave quantum optics. So probably you have already had in some talks about superconducting qubits and superconducting quantum computing. And my talk is also on superconducting qubits and superconducting quantum circuits, but with a little bit different perspective. So, so our superconducting circuits, like qubits and resonators and waveguide, are very useful tools for actually quantum optics, but quantum optics in the microwave domain. So, as you know, quantum optics has been developed in the optical experiment, but these days we can play quantum optics in the microwave domain on superconducting circuits. So I will introduce the cavity QED and waveguide QED in superconducting circuits. And then I'll discuss a few examples of the implementation of some functional devices and in this microwave quantum optical systems, like single photon detectors and generation and characterization of microwave photonic 1D cluster states, and also microwave one-dimensional quantum network. Okay, so I guess you can ask questions anytime during my talk. Just unmute yourself and ask me questions. Okay, so just a quick recap of superconducting qubits. I believe someone has already told you about this. So we are making qubits out of superconducting circuit. So probably the most the simplest circuit would be LC resonator connecting capacitance and inductance, and which gives rise to the harmonic oscillator. So in quantum mechanics, harmonic oscillator has energy levels equidistantly separated by the resonant frequency. And for realizing a qubit, this harmonic oscillator is a little bit inconvenient, because if you drive the resonance between the ground state and the first excited state, the second and third states are also on resonance. So it's difficult to keep the quantum state within the two basis states. So what we needed is a little bit of unharmonicity to make the energy levels non-equidistant. So for that, we use a Josephson junction, a tunnel junction between the superconducting electrodes, which works as a nonlinear inductor. So that makes this potential. This potential is actually comes from inductive energy stored in the inductance. So here, the Josephson junction as a nonlinear inductor gives this potential, but because of this nonlinearity, this is not harmonic. It's a little bit distorted. So that's why we obtain this non-equidistant energy levels in this circuit. And because of that, we can safely drive the transition between 0 and 1 states with a resonant microwave. So here we can realize such a circuit very simply, in a very simple manner. So we have two electrodes made of superconducting aluminum, and on top of the insulating silicon substrate. And then in between these pads, we have a narrow bridge, and in the middle of the bridge, there is a tunnel junction. So this is a sandwich between two electrodes. So there's a oxide insulating barrier in between the electrodes. So this works as a tunnel junction. And so this simple device is equivalent to this circuit. So and that this millimeter scale object works as a qubit or quantum two-level system effectively. So this sometimes we call it artificial atom. So in typical setup in superconducting quantum computers or circuit QED system, we often embed this qubit, which is sometimes called transmon, this qubit into a three-dimensional microwave cavity in a bulk aluminum. And then this system is described by this so-called Jaynes-Cummings Hamiltonian with a qubit two-level system and cavity mode, the harmonic oscillator, and the coupling term. So this is a canonical setup in circuit QED, circuit quantum electrodynamics. So we are going to use this kind of system for the as a stage, as a platform for the microwave quantum optics. Okay, so here, so this is our artificial atom, and the cavity plays. This is a cavity for microwave photons. Okay, so this the cavity QED, the cavity quantum electrodynamics, developed in atom optics system or quantum optics field in 1980s. Typically focused on the system where the photon is confined in a cavity. So, and the typical setup people are looking at is a so-called strong coupling regime, where the atom trapped in this cavity and interact strongly with the photon in the cavity. So strong coupling means the coupling strength between the atom two-level system and the cavity photon is much larger than other dissipation rate. So like a cavity decay or atomic decay or atomic dephasing. But recently, especially in microwave quantum optics in superconducting circuits, but also in quantum optics in the optical domain using photonic waveguide or nanofibers, people are also interested in waveguide system. So here we are more focused on propagating photons in a waveguide, interacting with the atom or artificial atom. So here the relevant parameters are first, this is spontaneous emission rate of the atom into the waveguide mode, either forward or backward, should be much larger than the decay rate to other mode, and also the dephasing of the atom. So in such under such condition, we can exploit the nice properties of this low dimensional photonic modes. Okay, so to see that, let's consider first an atom, say, floated in a vacuum. So here we suppose we drive the transition of the two-level atom with a resonant, say, laser beam, for example. And then the atom is excited, and then eventually re-emit the photon. But now the photon is re-emitted to anywhere around the atom. So obviously the optical mode, the incident mode, and the re-emitted modes are not mode matched spatially. So because of that, it's not easy to find, say, significant interference effect between the incident and the reflected, re-emitted modes. So, and also naturally the cross-section of the atom is very small, and so it's not so simple to find a nice interference effect in this resonant fluorescence experiment. However, if we consider an atom confined in a one-dimensional waveguide, the situation is quite different. So again, we excite the atom with a laser beam. Now it's confined in the waveguide, and the atom is excited and then re-emit a photon. But in this case, the re-emission only occurs into the forward or backward direction. So here, the spatial mode matching is kind of automatically obtained. And because of that, and due to the destructive interference of the, say, between the incident light and the re-emitted light, the forward scattering in this case is 100% suppressed. And in the end, we observe perfect reflection. This is a very simple system, but it's kind of surprising that even a single atom can reflect the light with 100% efficiency. So this is not so simple. It's still not so simple to do it with a single natural atom. Yeah. Any questions? Okay. So oops. Yeah. So but with in the microwave domain, we can relatively easily do that. So here, this is our experiment from 2010. So here, we put a superconducting qubit. In this case, flux qubit. You don't care what kind of qubit is. Anyway, just an effective two-level system coupled to the microwave coplanar waveguide on chip. And then we observe the transmission and reflection of the continuous microwave along this transmission line. So this is a transmission spectrum as a function of the external magnetic field applied to the qubit. So this in this flux qubit, depending on the magnetic flux threading through the loop, the qubit energy changes. So as you see here, at the qubit transition frequency, we see, if you take the cross-section here, we see very deep in the transmission through this waveguide. So this means that this artificial atom did reflect the incident microwave very efficiently, and again due to the destructive interference in the forward scattering, and because of that, it's almost perfectly reflected. And yeah, here the depth of the dip is about 94%, but later on with a better coherent qubit, we observed more than 99% suppression of the transmission. So in waveguide QED system like this, we can fully exploit the interference effect thanks to the special, say, perfect spatial mode matching, and obtain such a unique functions. Okay, so now we can apply this concept of waveguide QED and demonstrate different kinds of microwave quantum optical devices consisting of superconducting qubits and waveguide. So let me first discuss microwave single photon detector as an example. So here, our motivation is that how we can detect a single and itinerant and arbitrary waveform microwave photon and without destroying it. So, you know, photon detectors are commercially available for optical photons or photons in the optical domain. So yeah, for example, in avalanche photodiode, or more recently superconducting nanowire detectors, the incident photons are absorbed by this electrical device and then generate an avalanche of electrons, and then we detect the voltage signal as a click or as a count. And in a superconducting nanowire detector, when the photon hits this superconducting nanowire on the substrate, the superconductivity in the nanowire is broken by the energy of the single photon. And then it switches to the normal state and then produces a voltage pulse signal. So that's how we can detect it. Yeah, so it works pretty well for optical photons in the optical domain. However, the microwave photon has much smaller energy scale compared to the optical photons. So this kind of scheme do not directly apply to the detection of microwave photons because of the difference in the energy scale. And also, yeah, here, as you see, the photons are always absorbed and basically destroyed. And so that's not really non-demolition detection. Okay, yeah, so this is an illustration of the optical photons in the optical domain and the photons in the microwave domain. So it's really different size. So if you compare optical photons in the optical domain, say the communication wavelengths of 1.5 micrometer wavelengths photon to 10 gigahertz microwave photon. So 10 gigahertz corresponds to 3 centimeter of the wavelength. So the ratio is 20,000. So it's the microwave photon is has much smaller energy compared to the optical photon. So that's why we started to develop microwave photon detector, microwave single photon detector using superconducting qubit. So yes, superconducting qubit is a natural choice for this goal because it has a microwave energy scale, and then we can detect the transition in the qubit. So in the first experiment, we consider again one-dimensional waveguide. So this is a waveguide which is terminated with a mirror. So this is a semi-infinite waveguide, and we suppose to put a 3-level atom with a lambda type energy level structure. And suppose we have an incident single photon with some wave packet. And if this the carrier frequency of the photon is on resonant with this lambda system, this could excite this and yeah, like this. And then yes, as long as the bandwidth of the photon is much narrower than this transition. Okay, then if the transition rate from the upper state to the 0 state or 2 state are equal, then this kind of Raman type transition will take place with actually 100% efficiency. This is a little bit surprising things, at least to us. And how it could be possible? So here, yeah, we can think of 3 different possible processes in this system. So when the photon comes into this 3-level system, okay. First, the photon does not interact with this atom and then just reflected by the mirror. Or the photon is first absorbed by this transition and then re-emit back to the original state. So just elastic scattering. Or the photon is absorbed and then emit another frequency photon, and then atom relaxes into the other state. So there are 3 possibilities, but it turns out that the first 2 processes actually destructively interfere when these transitions are symmetric, have symmetric decay rates. So as a result, only this process takes place, and that resulted in this Raman transition with 100% efficiency. So this is a very, say, simple but very nice system. So we try to implement it with a real device. So yeah, and so initially we thought it's relatively simple to realize this kind of lambda 3-level system in superconducting circuits, but it turned out it's not so simple to achieve this symmetric decay in this lambda type 3-level system in superconducting circuits. So we decided to use rest state in a driven superconducting circuits. So let me explain that. So here we prepare superconducting qubit coupled to a superconducting resonator on chip. Okay, the qubit is here, it's small. And then as I showed you in the beginning, the coupled resonator and qubit system is described by the so-called Jaynes-Cummings model. So this is the lowest 4 level in this Jaynes-Cummings system. So G and E are the states for the qubit, and 0, 1, 2 are number of photons in the cavity. So so here the G0, E0, G1, E1 states create such 4-level system. But under some microwave drive on the qubit with a particular frequency, we can consider the rotating frame in the rotating frame, and then basically we can bring these 2 levels down by the driving frequency in the rest state picture. So we effectively obtain such a 4-level system in the rest states under the microwave drive. And here, because of the driving and depending on the power, driving power, we can tune the decay rate, for example, from this state to here or there, or this state to here or there. So here we have effectively the lambda system, actually 2 of this lambda system. And these rates are tuned by this drive power, and indeed we can find the condition where these rates symmetric. So that we call impedance matching condition because of the reason as I explained. So at the impedance matching condition, the microwave photon, the incident photon is 100% absorbed, and so like in impedance matched electrical circuit. So we use this as a kind of artificial lambda type atom coupled to the end of the input waveguide. So and we use this as a single photon detector. So here we observe the absorption spectrum of this artificial atom using the continuous wave microwave. So as a function of the drive power on the atom and also drive and the input photon frequency, we see 2 dips in the absorption or reflection spectrum in this waveguide. So here we see very strong absorption, more than 25 dB, so basically 100% photon is absorbed. And if you compare this spectrum with the theory, we can nicely reproduce that. And indeed, theory tells us that at this particular condition where we see this deep dip, the two transition rate are really equal. So this means that we have a symmetric lambda type 3-level system in this setup. So now we use this for single photon detection. So again, it's the same kind of spectrum. So here we have the dip of the absorption or dip in the reflection. So this is the absorption point. So here, so like this. So here the input photon is absorbed via this Raman type transition. And then, so we apply, weak coherent light as a, photon path signal, and then monitor the, after this absorption process, we monitor the state of the qubit, whether it's in ground state or the excited state. And then we found that the qubit is excited here. So, and this part, this region nicely corresponds to this absorption spectrum. So if you take the, if you compare this with theory, it's nicely reproduced. And if it takes a cross section here, we find that the photon detection efficiency in this experiment is around 66%. So the incident photon is absorbed by the qubit, and then we can read out the qubit afterward, and then find whether the photon has come or not. Okay, so this is the first example. And now I switch to the second experiment, where we use another setup for, in this case, okay, so in the previous experiment, it was still absorptive type experiment. So the signal photon is absorbed and destroyed. But here in the next experiment, we demonstrate non-demolition type detection. So again, the setup is very simple. So qubit embedded in a cavity. In this case, we use a 3-dimensional cavity like this. And so those qubit and the resonator is off resonant, about 2.7 gigahertz. And the coupling strength between these elements about 200 megahertz. So it's much smaller than the detuning. So in this regime called dispersive regime, we can rewrite the Hamiltonian here in this form with some approximation. So in this case, this shows that the interaction between the qubit and the microwave photon is this type. So this can be understood that depending on the state of the qubit, the cavity frequency is shifted, or depending on the number of photons, eta A, the qubit frequency is shifted by chi. The chi is called dispersive shift. In this case, about 1.5 megahertz. So yeah, so this is the same Hamiltonian, and so this is the experimental result. So here we connect waveguide or coaxial cable into this cavity. There's just a single port, and then measure the reflection from the cavity. So this is a reflectance, and for depending on the qubit states, either ground state or excited state. So as I said, depending on the state of the qubit, sigma z plus or minus 1, the photon frequency, cavity frequency is shifted by twice of chi, and because of that, the reflection, the phase of the reflected microwave is also shifted. So usually people use this mechanism for qubit readout. So qubit can be non-destructively read out by measuring the reflected microwave photon, a microwave signal. Okay, but here we want to use this for single photon detection. So this is the same system. So here, for example, if if the qubit is in the ground state, the incident photon will obtain this phase upon the reflection. And when the qubit is in the excited state, the photon will acquire different phase. Actually, in this case, shifted by pi. So this pi phase shift is obtained when the parameter fulfills this condition. The cavity coupling to the waveguide is equal to twice of the chi, the phase, the shift given by the qubit into the cavity. So then, okay, depending on the state of the qubit, the incoming photon is reflected with an opposite phase. So this is understood as a controlled pi phase gate, depending on the state of the qubit, acting on the incoming photon. And if for example, if you prepare a superposition state, 0 plus G plus E in the qubit, then, for example, if the incoming wave packet doesn't contain any photon, so when it's vacuum, of course, there's nothing happen. But if the incoming wave packet contains a single photon, now the phase of the qubit is flipped. So because this conditional pi phase gate is symmetric between the qubit and the photon, so here we interpret this conditional pi phase gate is acting on the qubit conditional upon the photon state. So by using this property, actually we can, okay, after this interaction of the wave packet with the qubit in the cavity, we can read out the qubit state afterward, and then find that whether the incoming wave packet contains a photon or not. So that works as a single photon detector. And also, because this is not absorptive and just reflective, so the photon is not absorbed and just reflected back. So this could be a non-demolition type detector. Okay, so let's see how it works in the experiment. So here in the experiment, we first prepare the superposition of a qubit by half pi pulse, and then input the weak coherent microwave pulse as say mimicking a single photon signal. And then after that, after the interaction, we apply another half pi pulse to rotate the qubit into the measurement basis, and then read out the qubit. And as a result, with increasing average photon number in this signal pulse, the qubit phase flip probability increases almost linearly. And this offset at the 0 photons gives a dark count of this detector about 1.5%. And then the slope, the initial slope, gives the efficiency, quantum efficiency of this detector, in this case, about 84%. So this is quite high efficient single photon detector. And of course, this is not perfect yet, and this is due to the internal loss of the cavity or dephasing of the qubit during the measurement, and also the mismatch of the copper, the cavity line width, and the twice of chi, the qubit phase shift. Okay, so this is a nice microwave photon detector, but we also would like to check whether this is a really non-demolition type measurement. So whether the photons survive after the detection. So here we did a conditional Wigner tomography, say, to analyze the reflected photon mode When the qubit says there was no photon, so qubit didn't detect any photon, then in the reflected mode, we find that it's basically vacuum. So this is a Wigner function. They say characterizing the photonic state in this wave packet, and basically this is a zero photon state with very high fidelity. And when the qubit says there was a photon, and then if we analyze this reflected wave packet, we find this is indeed mostly one photon Fock state. So with 84% fidelity. So it proves that this detector works as a non-demolition type detector. So we maintain the photon number states after the reflection. Okay, so and this could be also used as a heralded single photon generation. So when qubit says there is a photon, then there is always single photon reflected back. So we can use this as a single photon generator. Okay, so yeah, so this is a nice example of the waveguide QED. So and I hope you find that this could be a useful concept in this superconducting circuit and also in microwave quantum optics. Okay. Yeah, actually, indeed, this detector is not just a single photon detector, and this mechanism works for higher photon number in the input mode. Basically, so for 0 photon, 2 photon, 4 photon, this gives a zero phase shift. No, sorry, 0 photon, 2 photon, 4 photon input, the qubit phase is not changed. And if you have 1 photon or 3 photon or 5 photon or odd number of photons, then the qubit phase is flipped. So this is basically a parity, photon number parity detector. So by using that, actually, later the Zurich team demonstrated this parity detection, and also after the parity detection, the projection into the parity basis, the reflected wave packet will contain projected into a Schrödinger cat state. So that's also demonstrated in this paper. Okay, now I switch to another topics. So here we discuss the generation and characterization of one-dimensional cluster states. So actually, this superconducting qubit coupled to cavity or waveguide is known to be a very good microwave single photon source. It's kind of natural. We can initially excite the qubit and then let it emit into the waveguide. Then we obtain an itinerant microwave photon deterministically. So there are a number of schemes to realize the microwave single photon generator. But here I show you one example based on this paper in 2014. So here the qubit is embedded in again 3-dimensional microwave cavity. So again, this is a James-Cummings type system. So qubit coupled to the waveguide cavity mode, so 0 photon state, so 1 photon state. So here, in this, according to this paper, we can excite the qubit into the second excited state by repeating pi pulses, and then drive this transition called F0G1 transition. This can be driven by a strong microwave to induce the parametric transition here. And then once the state F0 is brought to state G1, so G1 state means qubit is in the ground state and cavity has 1 photon. And the cavity can quickly emit the photon into the waveguide and then bring the system back to the ground state. So this is a single photon generator. So here, by designing our device, qubit, and this is a coaxial type resonator in a cylindrical cavity and coupled to the waveguide. And by designing this, the coupling strength between resonator and the waveguide pretty large, we can actually emit the photon very fast. So here we achieve the single photon emission within 140 nanoseconds. So this is very short or broadband microwave photon pulse. Okay, so and now we can use this to generate more complicated microwave photonic states. So here we aim at generating one-dimensional cluster states by repeatedly drive this system. So here first we prepare the superposition of G and E and then excite it into E and F superposition, and then only drive the F0 state into the ground state by emitting a photon while keeping this E0 state. So this creates an entanglement between the qubit and the emitted photonic state. And we can repeat this process with a repetition time of 230 nanoseconds, much shorter than the relaxation time of the qubit. And so we can repeatedly emit a train of photons or entangled each other. And then so we can, in the end, create the so-called cluster states. Okay, so by doing that, so we emit a train of photons, and then we measure the photons, characterize the photons, photonic modes with a parametric amplifier and then a homodyne detection. We measure the quadrature of each mode and then take the correlation to obtain the density matrix of these generated cluster states in the waveguide. So here is an example of the 1D cluster state with 5 modes. And so this is a reconstructed density matrix. On the top right, we plot the argument of each element, and then on the bottom left, we plot the absolute value of the elements of the density matrix. So in the ideal case, the one-dimensional cluster state density matrix is like that. So we find that this is say well reproduced, even though this amplitude, for example, is not perfectly uniform. Okay, so and we found that the fidelity is about 62%. So it works nicely, but to scale up the size of this cluster state, basically we can create more and more wave packets in series. But for characterizing this large, the cluster states with a large number of modes is getting more and more difficult, because to characterize the density matrix, we have to determine the number of parameters scaling exponentially. And also for doing that, we need to measure the large number of correlations also scaling exponentially. So it's not easy to do that for a larger number of modes. So we look at the emission process again. So here, so this is a device, and we have some noisy operation on the device, and then here's a conditional emission process in this photon generation process, and then photon is emitted, and then again some operation in the device, and then conditional emission, the second mode, and then again so and so on. And we know that these photonic modes emitted sequentially are not really interacting with each other after the emission. So that makes the analysis a little bit simpler. So actually, we noticed that each process can be written with tensors, and so this creates a tensor network. And so this tensor network can be represented by the so-called matrix product operator representation. So and this simplifies the analysis. So so this is basically the product of these matrices, and then we can represent the emitted photonic states in this kind of form. And then the number of parameters we have to determine will be much reduced. And also, Theoris has proven that this matrix product operator states can be fully determined by analyzing local correlations. So it turns out in our case, we just need to characterize correlations between 5 consecutive photonic modes, and then eventually we can characterize the full density matrix in the larger chain of the photonic modes. So, so that's what we did, and so here, for example, we did this analysis up to 35 modes of the cluster states, and then estimate the density matrix by this square fitting. So this is a density matrix we obtained for the length 10 and length 35 of the generated cluster states. So even apparently the total fidelity of the large number of modes is exponentially small after 35 times of iteration. But still we find that the density matrix keeps some signature of the cluster states. And so here, because of this efficient characterization, we managed to do that up to 35 modes. But probably the total fidelity of this chain is not anymore so important, and more relevant would be the correlation between the neighboring modes. And here we characterize the so-called localizable entanglement. So characterizing the correlations, entanglement between the neighboring or relatively close modes. And we found that up to 6 consecutive modes can be still entangled in our experiment. So this is limited, of course, by the decoherence and imperfection in the system, but at least up to 6 modes, this cluster states maintains the entanglement. Okay, so our scheme of the characterization of this one-dimensional and cluster states has some advantage compared to the previously done the schemes previously demonstrated. So, of course, conventional tomography, quantum state tomography, scales exponentially, and for larger system, it's almost impossible. And in these references, people have demonstrated in the optical domain and microwave domain generation of one-dimensional cluster states and characterization. But there they assume that each modes are sequentially and identically generated. So, and in that case, the characterization is mostly okay, of course, very simple, but basically it's a kind of significant assumption. But in this work, we assume only that the photons are sequentially generated, and we didn't assume that each generation process is identical. But still, we can characterize these cluster states with a linear cost, and so basically we can extend the length of the cluster states even further. Okay, so this is the end of the second topic. So here we discuss the generation of the cluster states in this waveguide QED setup. Okay, so this is the final part of my talk. So this is still a theory proposal. Again, in the idea of microwave quantum optics in this one-dimensional net waveguide. Okay. So here we'd like to construct a quantum network between many quantum nodes connected along a one-dimensional waveguide. So here we have one-dimensional waveguide, and we have many quantum nodes. And each node can emit a photon and receive a photon, or transmit a photon without interacting programmably, and also in either direction. So it could be a one-dimensional quantum network with, say, all-to-all connection. We can communicate between arbitrary pair of in this network. Okay, so to realize that, we propose to use, say, 2 qubits coupled to the waveguide. So it can be considered as a kind of molecule instead of atom, because we now use two atoms as a one unit. So actually, it is simple to show that if we prepare such a bare state, the entangled state between in these two atoms with a particular phase, the emission from these two atoms into the waveguide result in again the interference in this waveguide, and with this particular phase of the bare state, the emitted emission will be constructively interfere on the right side and then destructively interfere on the left side. So in the end, this unit can emit the photon 100% into this right going mode. Okay, so this is a simple idea, but to implement it in the real waveguide, actually we found that this the simplest idea doesn't work properly. So this is because that in the presence of this waveguide coupled to these two atoms, there's a correlated decay into this waveguide, as I explained, and also there is an energy exchange interaction between these two qubits or two atoms via this waveguide. So because of the presence of the waveguide, these qubits actually interact through this waveguide. So that gives this exchange type interaction. So because of that, if we calculate the, say, photon emission process from this entangled state of these two atoms into the waveguide, it turns out that the photon is not really 100% emitted into this right going mode. And then we find that about 25% of the wave packet is emitted into the left unwantedly. And this is exactly due to this qubit-qubit interaction during this emission process. So some part of the qubit population, as you see here, the qubit population of the Q1 and Q2, starting from 0.50%, decays into zero, but in the middle, the population shows some oscillation. So that indicates that the population is transferred between the qubits. So that's why the interference is not perfect on the waveguide, and the emission is not 100% into the right going mode. So we found that we need to actually cancel out this waveguide mediated interaction between the qubits. So for that, we can introduce dynamic, time-dependent interaction between the qubits, and then dynamically tune that to cancel this time-dependent interaction between the atoms. And so if we do it properly, then we find that the photon is 100% emitted and nothing goes to the left. And then the qubit population also decays into zero without any strange behavior. So that would be the ideal case. Okay, so but this is a little bit too complicated to implement in the real device. So our idea is to replace, to insert an additional resonator between the waveguide and the qubit. And in this case, we don't really need time-dependent tuning of the coupling. So we just need a static cancellation of the waveguide mediated exchange interaction. Okay, but instead we need a tunable coupling, time-dependent coupling between the qubit and the resonator on both sides. And but if you do it properly, again we find that the initial state in the qubit, the bare state, results in the perfect emission into the right, and zero emission into the left due to the interference. And qubit also decays perfectly to the zero, say, empty state. Okay, so it works well. And so this is for the emission, but for the absorption, this is indeed a time reversal process of the emission. So suppose we have an empty node, and then there's a incoming wave packet, photon wave packet from the left. So then if we control this time-dependent coupling between the qubit and the resonator, we actually found that the absorption is perfect. Absorption of this photon is perfect at this quantum node. And then after the absorption, there's no right going or left going photon at all. So okay, of course, if the cancellation is not perfect, there's some residual reflection or transmission. But if we do it properly, there will be no say transmission or reflection. So perfectly absorbed. And after the absorption, we find that the qubit state, as expected, is the bare state with say, almost perfect fidelity. So this will be nice. And also, we show that if we keep this qubit resonator interaction to be zero, the incoming photon does not really interact with this node and just transmit it as we want. So so as long as the bandwidth of the photon is narrow enough, so broad, say if the pulse is broad, then the pulse is basically transmitted as it is. And of course, if the photon is too sharp, or the wave packet is too narrow or broadband in the frequency, there could be some distortion due to the interaction with this structure. But we are not interested in that regime. So as a function of the bandwidth of the photon, so if the photon is narrow, the bandwidth is narrow of the photon, or the wave packet is broad enough in time, the transmission is almost perfect, 100%. Okay, so these nodes can work as a deterministic emitter, receiver, or transmitter. So this is sufficient for creating one-dimensional quantum network. And so this is the device we have made. So here we have waveguide for the one-dimensional network, and then there are two resonators coupled to the waveguide, and the qubits are also coupled to the resonator. And here's a cancellation resonator for cancellation of this interaction between the resonators. So this is the device we are currently testing, but because of the imperfection of the device, we haven't demonstrated the result. But we hope by improving this device, we can really realize this quantum nodes for one-dimensional network. So again, this is a nice example of this interference effect in the waveguide, and could be very useful in future. Okay, so I think it's almost time, and let me before finishing, let me introduce our colleagues in the University of Tokyo and also in RIKEN. So some of them have already left, and so this work on non-dimensional detection is mainly done by Shingo Kono, who is now in Switzerland, and the cluster state generation is mainly done by Yoshiki Sunada, a student in the University of Tokyo. And the proposal of the quantum network is done by Nico Gerard, who is now in Tata Institute in India, and together with Shingo Kono. Okay, with the first experiment on quantum microwave photon detector is done by Kunihiro Inomata, who is now working in AIST in Japan. Okay, so yeah, this concludes my talk. So this is a summary, and so today I discussed cavity and waveguide QED in superconducting circuits, and demonstrated control and measurement of itinerant microwave photons in the waveguide using superconducting qubit and cavity as a tool for this control and measurement. And this kind of microwave quantum optics tools are pretty useful. I believe it could be useful for quantum computing or network, or also for quantum sensing. And here we discuss a few examples, but yeah, there are many other demonstrations and proposals, and I believe more to be invented. And so I hope some of you can in future join this field and create more fascinating ideas. Thank you very much for your attention, for listening.
Yeah, so there are a few questions in the chat box. May I read them for you?
Yeah.
Yeah, sure. So the first question is there any effect of relativistic Doppler effect on the working of the resonant two-level system?
Okay, relativistic. Yes. So within our experiment, we are not really. I think we don't really have to consider the relativistic effect, and I haven't thought anything about relativistic in our setup, and yeah, probably there is some possible experiment by using this thing in a relativistic regime, but yeah, at this moment I don't have any idea. Sorry.
There is another question. In the rotating frame, to satisfy the impedance condition, is there any effect on the photon polarizations and any effect on entanglement between polarizations?
Okay. Yeah. So in optics, yeah, people often use the polarization degrees of freedom, especially in a free space. The horizontal, vertical polarizations modes are degenerate, and also in optical fibers, you can still use polarization degrees of freedom. But here in microwave, especially in the coplanar waveguide on the substrate, the polarization modes are basically the degeneracy between the polarization degrees of freedom are lifted because of the structure of the waveguide. So we cannot really play with the polarization usually. So unless we specially design the waveguide or cavity or qubit. So in our experiment, basically we don't handle any polarization modes. So you can understand that we just use one of the modes only. It's okay?
So there is another question again by Deepan. Can vacuum photons form in the waveguide and alter the energy levels of the four-level system?
Yes. So okay, vacuum photons. I suppose it means vacuum, right? Vacuum of the photonic modes. Yes. So basically, the atoms, or say any level or two-level systems, four-level systems, embedded in vacuum, they are interacting with the vacuum. Yeah. So these levels actually renormalized. The energy spacing is renormalized by the interaction with the vacuum. That is called the Lam shift, and so there is the effect of the vacuum on these energy levels.
So there is another question by Avinash. How can we model a three-level system, that's Q-treat, out of n-level system?
Yeah, so it's say effective model. So of course we have many more levels at higher energies, but if we restrict our excessive energy, for example, we can effectively model this n-level system as a two-level system or three-level system. So in our experiment, of course, if we input very strong microwave pulse containing many photons, we cannot ignore the higher levels. We can be excited. But we consider the case where we apply only, say, pi pulse, half pi pulses at the, say, lowest energy levels, and also the input photonic signal is contains a very limited number of photons, basically less than 1. So that's how we ignore the higher levels and then pick the effective 3-level or 2-level system as a model.
So there is another question again by Avinash. What are the circuit equivalent of unitary operators that act on a 2-level system?
Circuit equivalent operators. Okay. So I suppose the question is like when we apply pi-pulse, how pi-pulse is the circuit equivalent means like Hadamard gate and qubit rotation and so on. Is that the question? Or, for example, for the QND detection, the interaction between the photonic mode and the qubit is like a control phase gate.
Thank you. So I have a small question. It's a bit of a vague question. Can be like PT-symmetric Hamiltonians experimentally used to do these things? Like you showed one slide where you used a directional absorption by using time reversal. So I was just thinking, have you tried experimentally using PT-symmetric Hamiltonians for these purposes?
PT-symmetric Hamiltonians, you mean? I think there are some proposals, maybe also experiments of using PT-symmetric Hamiltonians, so where we have gain and loss balanced. But in our experiments, we haven't introduced that. So, but in principle, you can consider that, I think.
Sure. Thank you, sir. Over to you.
Nakamura, I have a small question. The phase in your last, third one, the phase between excited state, ground state, can it be anything like exponential I-pi kind of thing? In your last page, conclusion, between the excited state and ground, is the one. That phase, can it be anything?
Excuse me?
That phase, can it be tuned? Can it be tuned instead of ±1? Can it be tuned?
Yes. So if we prepare minus pi over 2, then the photon is emitted to the other side.
I see.
So this can be This has to be tuned by other means. So, for example, in this device, these qubits are coupled via another resonator to implement a 2-qubit gate to create the Bell state, and the phase of the Bell state can be tuned by the control. So by tuning the phase, basically we can decide the direction of the emission.
Recently, I sent you the paper. This is York Stoller state. We are looking at the Wigner function and intensity correlation. And that phase showed very interesting behavior, particularly in intensity correlation. One can see clear signature for small photon number.
I see.
I'll send you that optics lectures paper. It just came out.
Okay, please.
Thank you for a wonderful talk.
Thank you.
Are there any more questions?
I don't see any questions now on the chat box and
so let's
the YouTube as well.
YouTube also there no more. So let's thank Professor Nakamura again for a wonderful talk and really bringing out the what the basic level research they are doing. Because I'm a theorist, it sort of became clear to me also. Thank you so much.
Thank you very much. Thank you.
So goodbye.
Right. Thank you.